Hey again, everyone. This time we've got another problem that deals with rotational motion. This one shows a rotational apparatus, or you can think of it as sort of a rotational variation on the Atwood machine if you prefer, where we have a hanging block with a mass of 0.05 kilograms, and it's tied to a string or a rope, which is then wound around a pulley and then wrapped around a solid vertical disc placed up on this tabletop. And we're told that the radius of this disc is 0.1 meters, and also that the the pulley is very small and lightweight and has no friction on it. Okay, so the first question we're asked here is to find the acceleration by looking at some sample experimental data. All right, so here is a copy of the graph that you were given with my best attempt at a best fit line drawn over it. So we want to try to estimate the slope of this line. Couple of things to keep in mind if you're ever doing something like this on an AP test. First of all, they definitely want you to show your calculation of the best fit line using 2 points on the line, not necessarily data points. So if your line happens to go right through a data point, then you can use that, but otherwise you should not be using data points for your calculation. Another thing is just more of a tip, as if you're finding yourself struggling to find grid points that the best fit line goes through and you're sort of having to eyeball it, pick 2 points on the line that are far apart from each other. That way, if the coordinates you pick are off by a little bit, it's going to have a smaller change on the slope than if you pick 2 points that are closer together. All right, so with that in mind, I'm going to just pick 2 points at the far end of my line here and try to estimate those coordinates as well as I can. This is part A, by the way. All right, so the point on the left has coordinates 0.25 seconds, and it looks like about 0.7 meters. And then the other point is at 0.55 seconds, and if I estimate that's maybe a fifth of the way between the last two horizontal lines, so let's say 1.55 meters. All right, so the slope of this line will be my acceleration, since this is a velocity versus time graph. So it's going to be 1.55 minus 0.7 over 0.55 minus 0.25. And that comes out to be approximately 2.8 meters per second squared. Now you may have gotten a value different from this depending on which points you chose and exactly how you drew your best fit line. So they will accept a range here. The range that they quote here is anything from 2.5 to 3.3 meters per second squared. All right, so part B, which, by the way, if you're still interested in knowing how many points each of these are worth, A is 4 points, B is worth 5. So B asks us to find the rotational inertia of the disk. All right, so for this we're going to have to write some equations based on this figure up here. So if I come back up here, I can think about the forces acting on the hanging block. There's a force mg pulling it down, and then tension in the string. And then up on the disk, there's just a single tension force here, which is going to create the torque that will cause this to rotate. All right, so if I write my Newton's second law equations, let me first define my positive direction. I'm going to treat down as the positive direction, since that's the direction in which the block will actually accelerate. And then I guess this would be counterclockwise viewed from above. That will be my positive direction of acceleration for the disk. All right, so for the block, my equation becomes mg minus t equals ma. And for the disk, my equation is net torque equals I times alpha. The torque would be tension times the radius, and that equals I times alpha, which since these two objects are connected by the rope, the acceleration is going to equal the linear acceleration divided by r. All right, so I have to put these two equations together. Let me just copy these down below. All right, so if I put these together, keep in mind we're trying to solve for I here. So I might take this equation and rearrange that so we get I is equal to tension times r squared divided by a. And then we know the radius, the acceleration is our answer from part A, so we just need to replace the tension with its equivalent from the equation for the block. So if I take this equation and rearrange it, the tension equals mg minus ma, or m times g minus a. So that means I can finally write the moment of inertia equals m times r squared times g minus a divided by a. And if I take my value of about 2.8, really 2.8333, and plug that in for the acceleration down here, plug in all of the other known values, then I get a moment of inertia of roughly 0.0012 kilogram meter squared. Again, there's going to be a range of possible values you get for this. So the solution guide gives 0.000985 to 0.00146 as their acceptable range. All right, and then there's one more sort of substantial part to this problem, which is part C. This one is worth 4 points. So C tells us to calculate the angular momentum of the disk at time t equals 0.45 seconds. So angular momentum, symbol L, is the moment of inertia multiplied by the angular velocity. So we know the moment of inertia from the previous part, so we need to find the angular velocity at t equals 0.45 seconds. So the angular velocity as a function of time is given by the general equation. It's whatever the initial velocity is plus alpha times t. We start from rest, so omega naught is 0. Alpha, the angular acceleration, will just be the linear acceleration divided by the radius. So we have a value for that. Or if we prefer, we can just say this is a over r times t. All right, so if we plug that back in over here, the angular momentum is going to be the moment of inertia times a over r multiplied by t. So if we put in all of those values, then we should get angular momentum of about 0.016 kilogram meter squared per second. And I believe there should be a acceptable range given for this one as well. But believe it or not, it looks like I'm not seeing one here. All right, so I guess to be consistent with parts A and B, there should be an acceptable range for these, but I don't have that calculated in front of me. But if your value of moment of inertia was within the acceptable range and your acceleration was within the acceptable range, then you should get an acceptable value for the angular momentum. All right, and then the final part, which would be the remaining 2 points, asks us what would happen if we removed the solid disk up at the top with a rim or a hoop that had all the mass concentrated near the rim. We're asked specifically, would the angular acceleration of the hoop be greater than, less than, or equal to the acceleration of the solid disk? So we have to understand where the angular acceleration comes from. So one way we can think about this is in terms of dynamics. So the angular acceleration comes from the torque that's applied to the pulley, and that's given by this equation, torque equals I alpha. All right, so if we replace the solid disk with a hoop, the moment of inertia is going to increase. So if the moment of inertia increases and the torque stays the same, which technically it wouldn't because the tension would change a little bit as well, but the first order, if there's no huge change in the torque, then if the moment of inertia goes up, then the angular acceleration should go down. So one other way of thinking about it is in terms of energy. So this system will convert potential energy into kinetic energy as the block falls. If we replace the solid disk with a hoop, then it has more rotational inertia, and it's going to need more energy to get it rotating. So we can also say larger moment of inertia is going to result in larger rotational kinetic energy for the same angular velocity. So if it takes more energy to get the hoop rotating, then there's going to be less kinetic energy for the block, which means the block is going to accelerate to a lower velocity. All right, so either way you want to explain it, the acceleration is going to be less for the solid hoop than it's going to be for the solid disk. All right, so this is yet another example of a problem with rotational motion. So hopefully you were all able to follow the main ideas behind this problem and the solution. If you have any questions, as always, please feel free to let me know. Thank you for watching.